Good afternoon, everyone. Welcome to the live session. We will wait for a few minutes for some people to join. We will start the session. If people join, they can join later. Welcome to the live session 11 for the NPTEL course Basic Environmental Engineering and Pollution Abatement with me Mahalakshmi S, Research Scholar from NIT-Trichy. This is the general information. This live session for the course Basic Environmental Engineering, Pollution and Abatement will happen every Saturday from 3 p.m. to 5 p.m. And you can join the class by using the Gmeet link MDI VDCP NCG. The same link can be used for every Saturday session. And all the live session videos are recorded and uploaded in the YouTube channel. The channel name is Mahalakshmi S. You can find it through at Mahalakshmi Shekhar and ATT. So in today's class, we will discuss the assignment 10 solution, and then we will see the overview of week 11 lectures. Then we have some sample assignment 11 questions and a few problems from the week 11 course. Okay. First, we will go to the assignment 10 solution. So this assignment 10, the first question is which of the following enzyme? Okay. The first question of assignment 10 is which of the following enzyme is or responsible for fermentation to produce the ethanol? So for the ethanol production, what are the enzymes involved? They are asking. So we know what is fermentation process, right? So in the fermentation process, what happens is the carbon content present in the ethanol is decomposed, sorry, in the biomass is decomposed and it is producing the ethanol. So in the ethanol production, what happens is the carbonaceous substances are converted into the ethanol C2H5OH with the help of the microbial organism. So why these organisms are important? Mainly what organism we are using in the fermentation process means we are using the yeast. So yeast cells are very important because it is supporting the conversion process of the biomass to ethanol. Mainly the enzymes produced by the yeast are the zymase and invertase. So these two enzymes are very much helpful in the conversion of the carbonaceous matter to ethanol in the fermentation process. So the right answer for the question which of the following enzyme is responsible for fermentation to produce ethanol is zymase and invertase. So option 3, both A and B is the right answer. Now, the next question is which of the following feedstock contributes to the larger production of ethanol globally? So, the question is globally. So, worldwide, they are asking which is the common feedstock used for the ethanol production. You know the answer, it is the coarse grains. Okay. So, coarse grains includes the maize and then rice stalk. So, all these sorghum, jawar, all these grain stalks are used for the production of ethanol. Globally, it is the major feedstock. Now, next question is the percentage of potash in boiler ash is around. So, in the boiler, it produces a lot of residues, and one of this byproduct is the ash. So, this ash component can contain many amount of minerals, mainly silicates, and among the mineral matter, potash is one of the very important thing which can be utilized from the boiler ash. For the agricultural purposes also. And this potash percentage in the boiler ash is around 14 to 22 percentage. That is the right answer. Wastewater generated in the copper smelter contains. So copper smelting industry is another type of industry where the oxide ores or sulfide ores are used to produce the copper oxide. So during the extraction, like purification of the ores, there will be a lot of components released from it. One of the major component is the sulfur oxides, right? So here, totally they are asking what could be the generated wastewater in the copper smelter industry contained. So it includes all of these materials. So it can contain the soluble metal compound, non-soluble metal compound, as well as the oil. So the right answer is all of the above. Boiler ash contains potash mixed with press mud and filtrate sludge to produce. So the ash produced from the boiler contains the potash that we know. Now when it is mixed with the mud and the filtrate sludge, the sludge material obtained after the filtration, these are all mixed together to produce which of the following item they are asking. Options are biomanure, biocompost, bio-oil, all of the above. The right answer is biomanure. So when the boiler ash containing the potash is mixed with the mud and filtrate sludge, it is going to produce the biomanure. Next question is skins and hides of the animals are treated to produce the leather by the process of. Okay, the presentation is not visible. No one has asked it. Sorry. I hope it is visible now. Entire screen is visible to you. Okay. So now the skins and hides of animals are treated to produce the leather by the process of cutting, boiling, tanning or cleaning. We know that in the tanning industry, one of the main components used for the conversion of the skins and hides of animals to produce leather is the tannin. So these are the natural tannins used earlier. Nowadays we are using the chromium during the tanning process. So the process converting the skins and hides of animals to leather is tanning. Okay, that is the right option. Next question is in India, around 74% of ethanol is produced from. As we discussed earlier, if it is globally the major feedstock for the ethanol production is the coarse grain. But in India, what happens? The major feedstock used is the molasses. So molasses is a byproduct obtained from the sugar industry after crushing of the canes. So this molasses is very helpful in the production of ethanol. That is the major feedstock in the case of India. Okay, when it comes worldwide, the answer is coarse grain. That is the major feedstock for ethanol production. Next question is potential source for leaks in the ammonia plant are find the most suitable option. So in the ammonia plant, what would be the potential sources for leakage? They are asking. Refrigeration loop, storage areas, flanges. So from all these parts of the industrial plant for ammonia gas production, so these all of the above refrigeration loop, storage areas, flanges, all are the potential source for the leakage in the ammonia plant. So the right answer is all of the above. Next question is tannery sludge is mostly so after obtaining the leather from treating the skins and animals of the animals, we are producing lot of wastewater. So when we are treating the wastewater from the tannery industry, finally after the secondary clarification, we are obtaining the lot of sludge matter from it. So these sludges are very important to be treated before disposal in any form. Like it can be just like that disposed, or it can be landfill, or it can be incinerated. But before that, the water should be treated. As we know that during the leather conversion, we are using lot of chromium. So chromium are the tannins used nowadays to convert the skins and hides of animal to leather. So removal of chromium is very important. So after treatment of the water, the produced sludge is disposed mainly in the form of landfilling. Okay. Next, coming to the final question of the assignment 10. The question is in an industrial biogas plant, food waste is anaerobically digested to produce biogas. The slurry contains 10% of solid food grains. The elemental composition of the food grains On a dry basis is carbon 50 percentage, hydrogen 5 percentage, oxygen 35 percentage, and nitrogen 10 percentage. So all of these percentages are given in weight percentage, that is mass basis. Around 90 percentage of the food grain are converted to biogas, and all the converted hydrogen forms the methane. So it is the hint given in the question. If the flow rate of the slurry is 3,500 liter per day, calculate the rate of biogas production. So we need to calculate the amount of CO2 produced and amount of CH4 produced from the process. Assume the density as 1 gram per cc. So among these options, the right answer is 467.25. Now we will look into the solution. So what are the data given here? So this is a biogas plant. So the feedstock used for the biogas production is the food waste. So food waste is anaerobically digested to produce the biogas, carbon dioxide and methane. In this one, the slurry contains 10 percentage of the solid food grains. So whatever the slurry we are using for the biogas production is going to contain only 10 percentage of the solid food grains they are telling. Okay. So only 10 percentage is the amount of food grain present in our slurry. And the elemental composition of the food grain. So carbon, hydrogen, oxygen and nitrogen content in the food grain is given in mass basis. And one more hint given is around 90 percentage of the food grains are converted to biogas. So we know that the flow rate of the slurry is 3,500. So initially 3,500 liters of slurry is flowing into the anaerobic digester. Among the slurry, we know only 10 percentage is the solid food grain content. So amount of solid food grain present in the slurry is 3,500 into zero point 0.1, which is 350 kg. Okay. Since the density is given as 1 gram per cc, that is equivalent to 1 kg per liter. So directly this liter is converted to kg here. Okay. So 3,500 into zero point 0.1, because only 10 percentage of the slurry is containing the food grain. That food grain only is going to produce the biogas. So initially the feedstock quantity is 350 kg. Okay. So in this 350 kg, what they are telling is this food grain composition is CHON, which is of 55, 35 and 10 percentage respectively. Okay. So what we need to find is among this 350 kg, what is the weight of the carbon, hydrogen, oxygen and nitrogen. So what we are going to do, just multiply the mass percentage here with the 350 kg. So 350 into zero point 0.5 is 175 kg of carbon present in the 350 kg of food grain. Okay. So 350 into zero point 0.05, that is 5 percentage, is 17.5 kg of hydrogen, which is present in 350 kg of food grains. Okay. Again, the oxygen is 35 percentage. So 350 into 0.35 is 122.5 kg of oxygen. Nitrogen is 10 percentage. So 350 into zero point 0.1 is 35 kg of nitrogen in the given quantity of food grain. Now, if you add this all together, it will give you the 350 kg. Okay. Now, one more data given in the question is among this 350 kg, we have found the CHON composition, but only the 90 percentage of the food grains are converted to biogas. So the efficiency is not 100 percentage. So out of the 100 percentage of our feedstock, only 90 percentage is converted to the biogas, they are telling. So we need to find that for the biogas production, what are all there? Mainly the carbon, oxygen, hydrogen. These are the components there, right? So first what we need to find is the amount of carbon converted to the biogas. So to find this, just multiply the zero point 0.9 out of this 175, because 90 percentage is only converted. It is 157.5 kg. And then amount of hydrogen converted to biogas is 90 percentage of 17.5 kg, which is nothing but 15.75 kg. With this, we have found the amount of carbon and hydrogen in the product, right? Now, with the help of the stoichiometric equation, we are going to calculate the amount of carbon dioxide and amount of methane produced. So to find this is the exact question asked. To find this, we are going to do the stoichiometric balance. Okay. So in this one, we know that CH14, the molecular weight is 16, right? So CH4, it is going to give you 12. plus 4 into 1 is 4. So 12 plus 4 is 16. So the amount of methane is 16. Okay. To produce the 16 kg of methane, we require 4 kg of hydrogen. Right. So here in the question itself, it is given all the hydrogens are formed into methane. So how much amount of hydrogen is converted to biogas means 90 percentage of 17.5 kg, which is nothing but 15.75 kg. So for 4 kg hydrogen, 16 kg of methane is formed. Then for 15.75 kg of hydrogen, how much methane is formed? Then we have to cross multiply and find it, which is nothing but 16 divided by 4 into 15.75, it will give you 63 kg. So for 15.75 kg of hydrogen, 63 kg of methane are produced now. And then the amount of carbon used for methane production. So we need to find the amount of carbon used. So for the production of 16 kg of methane, we require 4 kg of hydrogen and we require 12 kg of carbon, right? So now we are going to find the amount of carbon used. For the 16 kg of methane production, you require 12 kg of carbon. Now you know the amount of methane formed, which is nothing but 63 kg. Then if 16 kg of methane require 12 kg of carbon, then for 63 kg, how much carbon is required? So you have to cross multiply and find 63 into 12 by 16 is equal to 47.25 kg. So this is the amount of carbon required for the methane production. Now we know the amount of carbon used for the methane production. With this, you can easily find amount of carbon required for the CO2 production. Just by subtracting the total carbon converted to biogas with the amount of carbon used for methane production. So 157.5 minus 47.25 will give you the amount of carbon exactly used for the carbon dioxide production. Again, now for the carbon dioxide, we are going to do the stoichiometric balance. So it is CO2, right? So 16 into 2 is 32 and this is 12. So totally the weight of the carbon dioxide is 44, right? So for the 44 kg of the carbon dioxide production, we require 32 kg of oxygen and 12 kg of carbon, right? So these are the required items. Now we know 110.25 kg of carbon is used for the carbon dioxide production. So for 12 kg of carbon, with the 12 kg of carbon, we can produce 44 kg of carbon dioxide. So for 110.25 kg, how much carbon dioxide can be produced means just multiply the 110.25 into 44 by 12. You will obtain 404.25 kg. This is the amount of carbon dioxide produced. Now you have found the methane production and carbon dioxide production. Just add these two, which is 63 plus 404.25, totally 467.25 kg is the amount of biogas produced from the slurry in the anaerobic digester. Okay, so the right answer is 467.25 kg. Do you have any doubt? Any doubt so far? Okay. If no doubts are there, then we will move on to the week 11 content. Okay. So now coming to this week 11 lecture, we have the solid and hazardous waste management in this lecture. So the lecture 51 is about the classification of the waste totally and how the municipal solid waste are segregated, how they are treated and how they are going to be disposed. The overview of the solid waste management is given in the lecture 51. So if you are considering the solid waste, there are different type of waste like solid waste, liquid waste and gaseous waste produced each and every day. So the first thing is about the solid waste. So here in the solid waste, it is further classified into many types based upon the sources, right? So here, firstly, based on the source, based on different categories, this solid waste are categorized. Now, firstly, based on the source, how it is classified means domestic waste or municipal solid waste. So these are the wastes produced from each and every household. So mostly the domestic wastes are biodegradable in the nature. It is easy to treat them. Okay. And then comes the industrial waste. So industrial waste or the waste produced from the industries like the paper industry, fertilizer industry, sugar industry, like that from many industries, how the solid wastes are produced. And then the agriculture. So agriculture, like a lot of the agro residues are there after the harvesting period, right? So these wastes are coming under the category agricultural wastes. Okay. Next, based upon the biodegradability. So what is biodegradability? If there is a certain amount of organic content in it, then it can be easily decomposed and it can be produced into many other valuable products. Mainly based upon the composition only, we can find whether the product is biodegradable or not. That is what we are going to find in this biodegradable and non-biodegradable solid wastes. Okay, if they are not suitable for if they are not biodegradable, then it is not suitable for like a manure or compost production. It should only be incinerated and disposed of. Okay, for that we have to classify the wastes like this. Next is based on the combustibility. Okay, if the product is not biodegradable, means we are going to burn it. Then we are going to find whether the product is combustible in nature or non combustible. Combustible means in the presence of oxygen, whether it will catch fire and burn and it will liberate the heat energy, right? So we have to find the combustibility of the product, whether it is combustible or not combustible. Then we are going to check the compostability of product, whether it is compostable or non-compostable. Like with the help of the microorganisms, we can produce a very good compost rich in the organic content that can be served as the fertilizers for the crop growth. So that is one type of composting, and we can use the earthworms. So earthworm based composting is another type of composting which is called as vermicompost. So that is also very good manure for the crop growth. So based upon the compostability, it is again categorized into compostable or non-compostable. And then based on the usability, so based on the uses, like how these waste can be used, that is what the usability here means. So whether it can be classified into organic because of the high organic content, or it can be classified into recyclable, like we can recycle the product into any other usable form, or it can be an inert product. So inert product means that product cannot be converted into any other product, like we cannot use it in any other form. We can use it in the same form itself because it is inert in nature. It cannot change its nature. Okay. So these are the different classification of solid wastes, like based on the source, biodegradability, combustibility, compostability, and usability. We are categorizing the solid wastes into these many types. So coming to the India, so coming to the country like India, which is having the highest population in the world, right? You know, now India has surpassed the China in the population. We are the world's most populous country now in 2024. So here, with this many people, it has the higher rate of waste generation also. So per day, per capita of the waste generation is also higher. If you look into the composition of the municipal solid waste produced in India, it is like about 50 percentage is biodegradable. That is good only. So that we can easily reuse and degrade the product into any other usable form. And then around 20 percentage is recyclable. We can convert them into any other usable form. And then we have inert product for around 22 percentage, and all the other wastes include the 8 percentage. So this is the typical composition of the municipal solid waste generated in the India. Okay. Now coming to the some general terms like domestic waste, agricultural waste. As we discussed earlier, domestic waste are mainly biodegradable. So it includes the food residues, food waste, and then the tree trimmings from the gardens, and then the recyclable item. It is also recyclable, like it includes the paper, plastic, and glass materials. And the inert material include the stones and silt, which cannot change its property. Okay, it can be used anywhere else in the same form only. We cannot recycle them. in or reuse them in any other form. And then the agricultural waste, as we discussed, the agricultural waste or the crop residues, that is the agro residues, totally coming off from the agricultural field. So these residues are rich in their lignocellulosic content. Why this is important means this is the typical composition of any agricultural waste. So it will be having the lignin, cellulose, and hemicellulose. So all these are very important. It is having the good potential for the fuel production. Okay, you can convert them into bioethanol, you can convert them into biodiesel, you can also produce the gaseous fuel from them like a hydrogen production. So these many applications are there. So you can valorize the agricultural waste in any of these useful forms. Now coming to the solid management, we know that this much amount of waste, more than 600 million tons of agricultural waste are produced every year in India. So like this, apart from agricultural waste, also several tons of other wastes are produced in India. So how these solid wastes are together managed is one of the important thing. So firstly, the waste generated is collected through two different systems. One is the stationary container system. Another one is the hall container system. So this stationary container system, we know that we have the collection tanks, like a waste collection tanks near every household. So from this tank, we will be putting the wastes, and from this tank, these wastes are collected to the storage site. So it will be going to the storage site, and then it is treated one by one later. But in the case of hall container system, directly it is not going to the storage site. It is directly going to the processing plant. And then the empty cans only come back to the storage site. Like that, that is the difference between the stationary container system and the hall container system. Now, how these wastes are segregated at the source itself, how these are managed, if you see means, these are segregated into recyclable item, and then organic fraction, inert material, and hazardous wastes. If you look into the recyclable item, then they will check whether it is combustible or non-combustible. As we discussed earlier, combustible product or the metals and glass substances which can be recycled or repurposed, and non-combustible materials includes the plastic based products, okay, that can only be recycled, okay, into any other form. And then organic fraction include the biological treatment. As we discussed, if the organic matter is rich, it can be composted with the help of microorganisms or living organism like earthworm. So after biological treatment, the product will be obtained and used in any other form. And now coming to inert material, inert type of waste, like I said, the gravels, sand, stones. So these materials can be used for the low grade construction since they cannot be converted to any other form. It can be it can be used for the low grade construction activities. And then coming to other category, hazardous waste. So hazardous is that this waste is very harmful, like the disposal is very much important. So what we are going to do is we will mostly prefer the incineration method in the case of hazardous waste. If it is a radioactive, if it is having radioactive waste substances and all, then those will be landfill. So class 1 hazardous waste type are mostly landfill deep into the ground in any segregated zone in the earth. And then the next class of hazardous waste are mainly combusted, pyrolyzed, or incinerated. Like this, these waste substances are disposed of. So now, some other disposal method in the solid waste management include open dumping. So open dumping is initially we will put them on the surface. So what happens because of the microbial action, because of the temperature and pressure, these substances, somewhat rich in organic content, will naturally decay and decompose and transform into the soil itself. And in the case of landfilling, when it cannot be treated at all, then we will bury the ground and deeply we will fill the lands. And then disposal in the solid surface. So on the ground itself, we will be disposing, barging into sea. This also happens. So many waste products are barged into the seas. which is affecting the coastal life also. So after the particular treatment of the waste only, these can be allowed to barge into the seas. And then coming to feeding to hogs. So this is another method of the solid waste disposal. So in these categories, mostly they are recycled or repurposed. But one of the major waste which is very difficult in management is the plastic. So why this plastic is very difficult to manage? Because their biodegradability is very, very, very less. It takes millions of years to decompose a single plastic bag, right? So this plastic management is very crucial. So for that only, what the government is saying is, before the plastic production itself, follow these 5 Rs. Okay, for the plastic waste management. So the first one is refuse. On the first hand, it is always advised to refuse the use of plastic. Don't use the plastic material. Okay. So in case if we are using it, then reduce the consumption of the plastic waste. So reduce the consumption in the day-to-day life. Instead of plastic bags, use some biodegradable bags or reusable bags like that, and then reuse it. Reduce its consumption, and then don't throw it immediately. Don't buy the one-time usable plastic waste products and all. So you reuse the plastic waste again and again until it is losing its integrity. Okay, and then repurpose. So repurpose is if, for example, if you are having a water bottle, like a plastic water bottle, we can reduce its usage. Initially, you are not allowed to buy it, right? To save the earth means we should not use the plastic bottles and all. So plastic bags, plastic bottles, these are the typically used items in our day-to-day life. We can reduce its consumption itself. Firstly, after buy, in case you have bought the plastic bottle, you can use the same bottle instead of purchasing 4 to 5 bottles. Limit the buying of the bottle. Once you have bought it, use it until it loses the integrity. Use it again and again. After some point of time, you cannot use the bottle for carrying the water. Okay, sometimes the lid might be broken. So at that time, what you can do is repurpose. So this repurpose is also called as upcycling. You might have heard about the term recycling, but this upcycling is also one another way to efficiently manage the all kind of waste materials. So what this upcycling means, instead of carrying water to college or schools, you can use the same bottle for growing the plants. So that is the repurpose, like you are giving some other useful nature for that particular plastic bottle. That is what repurpose or upcycling. So that can be done. Once that is also not enough, it is broken, nothing can be done with that bottle means, then you can go for recycling. You can submit it. The process will happen. Again, this plastic material can be used to produce one another plastic. So this is the 5R, very important in the waste plastic management. So it is always advised to limit the use of plastic material in any forms. Okay. So now coming to the lecture 52, this is about a different methods of the waste disposal. So this lecture is about the incineration. So this incineration, as we discussed, most commonly incinerated waste or the hospital waste, since those are very hazardous in nature, and the blood tissues, sometimes all the syringe needles and the medicines. So all these materials are to be incinerated to avoid the spreading of diseases, right? So incineration is nothing but the combustion of the material, waste material, so that the heat energy will be produced in larger amount. That's why this kind of method is termed as exothermic reaction. The ultimate products are formed during the incineration of the waste materials or the gases. You'll obtain a lot of gases like carbon dioxide, carbon monoxide, and then nitrous oxide, sulfur dioxide. It is all about the amount of air involved during the combustion process. You can obtain the fully converted gas material or partially converted gases like carbon monoxide and all. And then the ash. So the ash material produced can also be tested for its components, mineral content, and we can check whether if the heavy metal content is very less, then we can use it for any other purposes. Okay. So the number of steps involved during the incineration is drying. First is drying. Drying of the waste material involves the removal of the moisture content in our waste material. And then comes the pyrolysis. So pyrolysis we will look in detail in the following lecture. So in brief, pyrolysis is the uh, burning of the waste material in the absence of the air so that uh, the degradation of the waste material happens to some extent in this process. Then comes the combustion. So initially in the oxygen limited atmosphere it is burned. Next in the oxygen rich atmosphere, when it is burned it is called as the combustion process. These are the steps involved in the incineration, and always to ensure the complete combustion, because the incomplete combustion will release many hazardous gases, right? For that only we are using the complete combustion mode during the incineration process. To ensure the complete combustion, we will be doing a stoichiometric balance, like for this much amount of the waste material, how much amount of the would be the typical composition of the waste material, and how much amount of oxygen is required for burning of the waste material. With that only, we will come to a conclusion how much air is to be supplied. And since the exact percentage of the carbon, hydrogen, nitrogen, oxygen in the waste material will not be known. So, to ensure the complete combustion, we are keeping a excess air supply. That is always a 5 to 50 percentage. In this range, the air is provided in excess quantity to assure the complete combustion of the waste material. And the performance factors. So, the performance of converting the waste material into the gas, completely combusted gases depends upon the contact time. So how much time it is there, what temperature it is providing, and what is the turbulence in the waste material. So all these are going to affect the performance of the incineration process. And if you see, this is the conventional combustion process. So where this grating tray is allowing the fuel, that is our feedstock waste material, to go inside the reaction chamber, and air is supplied here. So both air and biomass is fed here. So what is happening is the combustion of the waste material happens. Okay. So this is further classified into two types. Okay. One is the air staging and another one is the fuel staging. These are the two different stages that can happen in the incineration process. So two types are there. So what is air staging? As the name indicates, air staging is we are providing air in two stages. Okay. So the first stage is here. Initially, the waste materials are fed here at the bottom of the reactor, and then there comes the reduction zone here. So here again the secondary air is provided. So the primary air is provided in the stoichiometric ratio. That is very important. So it is always in the stoichiometric ratio level. Okay. So initial combustion happens here, and then in the reduction zone of the furnace, we are providing the secondary air here for the further reaction of our waste material. Okay. In the fuel staging, we are staging the input of the fuel. Initially, the fuel is given here. Okay, and then on the secondary stage, in the reduction zone also, we are providing the secondary fuel here. Okay, here what is the difference is uh, here it is less than 1. It is less than 1 means it is in the stoichiometric level. But here always in the fuel staging it is greater than 1. It is always greater than the stoichiometric requirement. Like excess air is provided in general in the fuel staging process. Okay. These are the two types of staging involved in the incineration process. Now coming to the process flow. So what this process flow involves means first step is sorting. So sorting means we know categorizing, right? So why the sorting is important when we are burning it, if some big particles are there, bulk materials are there, and some small particles are there, then the uh, capacity of heating the different materials are varying in the reactor itself. So there can be a quenching of the heat. Like say for example, the bulk material is in the middle and small materials on the top means then for the heat supply rate will not be homogeneous, right? So for that only, initially itself we are sorting the waste materials. Say for example, the bulk waste material, we cannot categorize them exactly, like the uniform size material cannot be exactly separated, but we can sort out the bulk waste material separately. And now homogenization. So in between, we will be mixing the waste material to avoid the larger particles. And then comes the shredding. So shredding, we can use the cutting mill for shredding in the large scale also. So it will be somewhat shredding the waste material into uniform size, but this shredding is not mandatory for incineration. It can be done or it cannot be done. Okay. Now comes the incinerator. So in the incinerator only we are providing the air. So our fuel is our waste material. So in the presence of air, what is happening is burning of the waste material happens. So it is going to release a lot of energy. If you see, it will be more than 900 degrees Celsius typically. So it will be minimum above the 500 degrees Celsius. It can reach about 900,000 or above 1000 degrees Celsius also while it is burning. So much amount of heat energy is released while burning of the waste materials. So we cannot just like that allow the heat energy to get lost into the atmosphere. So what we can do is we can recover the heat energy during the incineration process. So this heat energy, like a hot gas, can be converted into steam. So after converting the hot gas into steam, that can be sent to the boiler, and these steams can be helpful in rotation of the turbine, and it will be further converted into electricity. Or these steams can be sent to some industries which require the steams during its process. So as the industrial stream, also we can recover this heat energy, or for electricity generation in boilers, we can recover the heat energy. Somewhat we have to recover the heat energy produced during the incineration process. Now, coming to the classification of the incinerator or combustor, there are different types of incinerator. It includes the fixed bed, rotary kiln, and then the fluidized bed. So, as the name indicates, in the case of fixed bed, it will be like this only. So, we have the fixed bed of inert materials here. So, it is completely packed with the materials, and then we are passing the air here and supplying the air, and then the burning of the biomass happens. So all these are happening in the fixed bed. Okay, this bed is fixed bed. Now in the case of rotary kiln, so as the name indicates, this is the rotary kiln. So if you see, the materials are fed from the hopper here, and it is going through the tray like this, in this way. And what happens is, from the burner, the heat energy is supplied in this direction. So this tray is a steel tray. Okay, it is a rotatory tray. So it will be rotating in the horizontal axis. So the mixing happens here, and the heat energy is passing here. So burning of the material is happening here, and the exhaust gases are venting out here through the exhaust, and whatever the product is formed, like ashes, gases is collected here, and the ashes and the rust and burn particle, all these will be typically collected down here. Okay, so this is the working of the rotary kiln. And in the case of fluidized bed, since fixed bed is the fixed matrix, so fluidized bed is all the materials will be fluidized in nature, like it will be circulating or it will be bubbling. So those are the two types of fluidized beds. So if you see, this is a fluidized bed. So here all the materials are filled in, and the hot air is passing here inside the chamber. So here, after burning, in the each step, we will be seeing the drying, pyrolysis, and combustion. Finally, the completed output gas, that is a flue gas, will be collected here, and whatever the residues formed will be removed later. Okay, this is what happening here in the fluidized bed. So these are the different types of the incinerator: fixed bed incinerator, rotary kiln, and fluidized bed, and mainly the flue gas cleanup. This is one more important step. Since we are burning the waste material, it is not going to form the clean gas itself. Okay, so these flue gas will also contain the unwanted gases like nitrogen oxide and then mercury dioxide. So dioxin and furan formation is very dangerous. So this removal is also very much important. Acidic gas. So acidic gas form should also be removed, And then the particulate matter removal. We know that inhaling of the particulate matter from the contaminated atmosphere is going to cause a lot of ill effects in the human health. So the particulate removal is also very much important. So after the recovery of the heat, during the process itself, we have to clean up the flue gas. That is also very important in the incineration process. Okay. So next we have gasification and pyrolysis. So gasification is nothing but combustion of the carbonaceous feedstock into the combustible gases. So here we will be providing the oxygen supply. In partially we will be providing the oxygen supply. Like there is not only the reduction zone, there is a combustion zone, but only a limited amount of oxygen is used. So that the carbonaceous feedstock will be converted into the gaseous products they are telling. And the byproduct obtained from the gasification is the char. So this char is also called as the biochar, and it is also having many advantageous properties in agriculture. And then it can be used as a coating material in the supercapacitors. And since it is a kind of activated carbon, it can also be used for cleaning of the wastewater. It can be used as an absorbent. So a lot of applications are there for the biochar. And now, but biochars are the byproduct of the gasification process. The major products involved are the carbon monoxide, carbon dioxide, hydrogen, and methane. Okay, these are the major products involved during the gasification process. And one more thing is the gases produced during the gasification is called as a syngas. So it is called as syngas if we are using oxygen as the combustible gas. Okay, sorry, oxygen as the combustion agent. Now, if air is passed, or if we are using the steam instead of oxygen and all, then the gas is produced is called as the producer gas. Okay, if pure oxygen is used for the combustion process, then the produced gas is called syngas. Okay, when air is used along with this, we will be having the inert nitrogen, or if there is an incomplete conversion happening, means we'll have a nitrous dioxide or nitrogen dioxide, like that, nitrous oxide or nitrogen dioxide as the byproduct along with the fuel product. Okay, so the major steps involved during the gasification process are drying. So we know when it reaches the 100 degrees Celsius, the drying of the waste material occurs, and then comes the devolatilization. So all the volatile materials will be getting evaporated. So uh, reduction of the waste material happens generally there. Now, with the presence of partial air supply or oxygen supply, oxidation will happen. So that what happens is initially, if this is a solid particle, drying happens, and then because of the reduction process, there will be somewhat pore formation. Following by that, what happens? Oxygen is passed. So when oxygen is passed into this solid particle, what happens? Oxygen is going to penetrate in and out. So again, because of the oxygen, what is happening means some amount of substances are liberated as carbon dioxide, carbon monoxide, like that. So oxidation will increase the amount of pore size in the solid particle. Okay, so pore size will be increased because of the reduction and subsequent oxidation process. So this is the major difference between the gasification and pyrolysis. Like there will be a reduction process with the subsequent oxidation process. So the pore size will be higher. And this is also a self-sustained process like any other method. Like in the incineration and all, we will be providing a lot of air for burning. But here in the gasification process, when in the reactor, the biomass is packed tightly in this manner once you are supplying the air and once the heating is done. So from the top, if the heating is happening means then for the next layer burning, the initial layer itself will act as a heating source. Okay, so this is a self-sustainable process. That is also one of the advantage of the gasification, and it has another advantage, like if we are providing the oxygen in equivalence ratio, so it can be easily replicated in large scale. So whatever is done in the gasification reactor can be also repeated in the large scale to produce the same quantity and of the product in the same quality also. So this is a scalable one. That is the advantage of the gasification process. And then after the devolatilization and oxidation, ash cooling is happening. So we'll be passing the inert gas like nitrogen for cooling of the reactor. Once this reactor is cooled, complete shutdown of the oxygen happens. So whatever the remaining unburnt product is there, like the char product is formed after the ash cooling. Char and ash will be there. Okay. And now the factors affecting the gasification. So during the gasification product, many useful products are formed. What are the different products that are going to affect the gasification, or um, different factors going to affect the gasification or the feed injection? So how our feed means the biomass, that is the waste biomass, how we are going to give the input to the reactor, whether it is a counter current or cross current. Okay, the type of feed injection, and then what type of gasification agent we are using, whether we are using the pure oxygen or air, and then the type of heating, like direct heating or indirect heating, and then what is the temperature range and what is the pressure of operation. So all these factors are going to affect the gasification process. Okay, now these are the different types of gasifier. We will see them one by one. The first type includes a fixed bed. As we have seen the fixed bed type in the incineration, so here also the matrix is fixed, like in the reactor, it is completely packed with the waste materials. So the bed is fixed in nature. Okay, and here in the first one, this is the updraft gasifier. So what is the difference? I will tell you. So here the biomass is fed from the top, right? So biomass is fed from the top and air is supplied from the bottom of the reactor. Okay, this is the grate fixed at the bottom. Okay, and air is fed from the bottom, and whatever gas produces collected from the top. Okay, so this is what happening in the draft gasifier. So the counter current flow is happening. Air is supplied from bottom and biomass is fed from the top and gas is collected from the top. Okay. Now, in the downdraft gasifier, if you look at this, here also the biomass is fed from the top. Okay, but instead of supplying air from the bottom, so the air is passed from the sides of the reactor. So what happens? The concurrent flow of is going to happen here, and whatever the gases produced are collected from the bottom of the reactor through the tubes. Okay, this is what called as the downdraft gasifiers. Commonly used one is the downdraft gasifiers. Okay, and then because since the air is fed from the middle, it can circulate to the top and bottom also. Okay, so it will be very effective for ensuring the complete conversion. And now coming to the next category, fluidized bed. So the matrix is fluidized. So it can be a bubbling one, so that our biomass will be bubbled up in the presence of air or oxygen. So here air is supplied from the bottom of the reactor and biomass is initially filled in the presence of the air or oxygen. It is bubbling here and whatever product produced are collected from the top. Okay. And now this is the circulating fluidized bed. So circulation of the biomass, circulation of, happens here, not biomass, the energy from the biomass. So now here we are supplying the air or oxygen or steam from the bottom. Biomass is again here fluidized. So whatever the same gas produced is collected from the vent here. Okay, so it is passing through the circulation loop. So these gases are again recirculated, and these gases can be again used for the conversion of the biomass into gaseous product. Again and again, like this circulation is going to happen. In between, the converted syngas is also connected. So now in this dual fluidized bed, we have a combustor separately and we have a gasifier here. So here with the presence of air, what is happening is the combustion of the biomass happens, okay, and all the completely converted gases are passing here, and then it is coming to the gasifier. So this gas is also used along with the steam for heating of our biomass. So gasification happens. So syngas is collected from the top of the gasifier here, and the some of the gas is again recycled back into the combustor. So again and again, initial preheating type of combustion is happening here, and whatever gas is produced is helpful for gasification. That is the point here. That is what happening in the double fluidized bed reactor. And now next type is the entrained bed. So in the entrained bed, what is happening here? The biomass is fed from the top. Oxygen is also fed from the top. Okay. And now if you want to supply steam, steam is also fed from the top. Everything is fed from the top. After the complete conversion, the slag and the syngas are collected at the bottom. So here the syngas is collected from the bottom. So what is happening here is following the biomass, the oxygen is supplied here. That is what entrained is meaning. So one after the other, it is supplied. Okay, so in first the biomass, then the oxygen and steam are supplied, and then the conversion happens. Finally, the syngas is collected from the bottom. And now coming to the plasma gasifier, what is happening here means biomass is supplied on the top with the help of the plasma torch. So plasma is the fourth state of matter, right? We have solid, liquid, gas, and another form nowadays it is called as plasma. So plasma torch is used for heating of the biomass, and finally the syngas is collected from the top of the reactor. So these are the different types of gasifier or gasification reactors used for the conversion of carbonaceous waste materials into gaseous fuels. Okay, in the presence of partial oxygen. Okay, this is what about the gasification. Now we will move on to the next lecture. Lecture 54 is about pyrolysis. As we discussed earlier, there is only one major difference between the pyrolysis and gasification. Initially, most of the conversion happens with the help of pyrolysis method only. Nowadays, only gasification is used widely because of its advantages as discussed earlier. So here the decomposition of the carbonaceous matter will happen in the absence of oxygen. Okay, that is the important thing. And the major products formed include the char, biochar, bio oils are also produced in higher quantity. If you see here, mainly gases are produced and to somewhat the biochar is produced. But here, one of the other main product is the bio oil. Okay, by adjusting the stoichiometric ratio, we can influence the percentage of char, percentage of bio oil, and percentage of gases in the product state. Okay, so by using the stoichiometry, you can increase the oil yield, or you can increase the char yield, or you can also increase the gaseous yield. Okay, the gases formed include the carbon monoxide, carbon dioxide, methane, and hydrogen. Now the factors affecting the pyrolysis or the temperature, residence time, how long the biomass is staying there, and what is the heating rate, what is the size of the feedstock we are using. So all these are the major factors affecting the pyrolysis process. Next, as we discussed, one of the main product formed in the pyrolysis, which is not produced much in the gasification, is the bio oil. However, the bio oil formed in the pyrolysis, when we are comparing this bio oil with the diesel, it will be having the higher water content in it. And then it will also have some high oxygen content, and viscosity will be higher, but it is having low heating value. Since the presence of water is higher in it, heating value of this bio oil is very less. So what we can do is we can upgrade the oil, like we can use some treatment methods to upgrade the quality of this bio oil to improve its efficacy. Okay, so now one of the method is physical method, in which we can filter the oil, emulsify it with the hydrocarbon, and we can add some other solvents to ensure to increase the heating value of the bio oil. And then the chemical method, here the reaction with some other alcohols can be done so that its heating value can increase. And then the catalytic deoxygenation. So some of these methods can be used for upgradation of the bio oil produced in the pyrolysis process. And one of the other major product compared to the bio oil, other major product produced during the process is the biochar. So the char obtained is rich in carbonaceous substances. As I said, it is more like the activated carbon. Okay, so it can be used as the adsorbent agent for cleaning up of wastewater or many other treatment process. And since it is having the high amount of carbon content, it can be used as a fertilizer. So it can be used as a natural fertilizer. It will be having a good cation exchange property. It itself will have some amount of NPK, nutrient content, some micronutrient content. But we have to check the heavy metal present in the biochar, because our feed is the waste material. It will be having some heavy metals. So we need to check the heavy metal content in it before applying it as a fertilizer. Since it is having the higher amount of carbon, and our soil nowadays are less in the organic carbon content, so these carbon can replenish the soil, and it can also capture the carbon dioxide in the soil. It will also prevent the leaching of the soil, improve the nutrient retention capacity. So numerous advantages are there in using the biochar. Okay, so this is having versatile application. Now, if you see the mechanism of pyrolysis, so this is the different phases involved in the pyrolysis process. So in the primary phase decomposition reaction, it is a very short reaction, okay, whether the biomass can be converted into char or gas products. So mainly it is going to give out some volatiles, okay. In the secondary phase only, the cracking and condensation occurs. Because of that, the oil is produced, and then some other gases is also released. First is the char formation with gases, and then the oil formation with gases. Finally, this bio oil can also repolymerize to form the char gases and some leftover amount of bio oil. Okay, so this is the different phases involved in the pyrolysis process. Now, one of the major waste that can be converted with the help of pyrolysis method is the plastic. As we have discussed that plastic management is very difficult. So pyrolysis of the waste plastic is one of the widely explored method. So these plastics are pyrolyzed to obtain the liquid, gas, and solid products. Okay, so that is what we discuss now. So that liquid product includes the liquefied petroleum gas or fuel or lobs, waxes, hair oil, and like many product can be formed. And all the gases obtained during the pyrolysis of waste plastic can be used for heat application. And then the solid products, that is the char formed by the pyrolysis of plastic, can be used to form the carbon nanotubes. So these are also very much used in the nanotechnology side. So these carbon nanotubes are having better properties than the conventional one. Okay. Now, this is a process flow of waste plastic recycling. So if you see, the feedstock is clean, dried, and size reduced. So we know that we have to remove the bulk particles, make it as homogeneous and uniform in size, and then heat is provided so that the melt feed is here. Okay, so the melt feed is here. It is sent to the pyrolyzer. So because of pyrolysis process, where the decomposition of the carbonaceous matter occurs, and then it is distilled. Okay, after distillation, the gases are sent to the gas scrubber. Okay, and it is again passed out here. And now the main products involved are gasoline, and then the kerosene, then the diesel, and the byproduct or another product obtained from the pyrolysis process is the carbon char, nothing but the biochar. Okay, this is the process flow of recycling the waste using the pyrolysis process. I hope there is no doubt. Do you have any doubts so far? Any doubts so far? We will move on to the assignment 11 sample questions. So the first question is which of the following is not considered as biodegradable solid waste? So we know that biodegradable is rich in organic content, right? So foodstuff, plant waste, animal waste, plastic. So it is very easy. The right answer is plastic. We know that food waste, plant waste, animal waste, all these things will contain the organic fraction in it. So it is biodegradable. And plastic is the non-biodegradable waste material. Select the thermochemical route used for the production of energy from the waste. Solvent extraction, fermentation, pyrolysis, and hydrolysis. So, what is the thermochemical route used for the production of energy from wastes? Thermochemical route they are asking. The right answer is pyrolysis. So, pyrolysis is the thermochemical conversion. Pyrolysis, gasification, all these things are thermochemical conversion method. It is using the heat energy for the conversion of the waste material. Next is the select the treatment process that involves the combustion of organic substances. So, which treatment process involves the combustion of organic substances? So, which process involves combustion? Incineration, distillation, solvent extraction, anaerobic digestion. Combustion is burning of the substances in the presence of oxygen. The right answer is incineration. Okay. Here only the carbonaceous matter are combusted to produce the gases. Depending on the fuel properties and system configuration, the typical exhaust air required for various combustion systems is in the range of. So, to ensure the complete combustion process, we are using the exhaust air. So, what is the exhaust air percentage? We have discussed this. The right answer is 5 to 50%. There's a general range of exhaust air supplied to ensure the complete combustion during the process. Fischer-Tropsch synthesis is normally used to convert syngas into. We know that during the gasification process, if we use the pure oxygen, we are going to produce many gases, which is called as syngas. The syngas can be converted into which type of product? Gaseous fuel, liquid fuel, producer gas, solid fuel during the Fischer-Tropsch synthesis. The right answer is liquid fuel. We will convert the gaseous fuels like carbon dioxide, methane, and then carbon monoxide, hydrogen, all these things into liquid fuels by the help of Fischer-Tropsch synthesis process. In the gasification process, when air is used in place of oxygen, the produced gas contains a high amount of nitrogen, sulfur, hydrogen, oxygen. It's very simple. If you use the pure oxygen, the product will be carbon dioxide, hydrogen, carbon monoxide, so all these things, and also methane. If you are using the air there, then only the nitrogen will be present in your product as nitrogen dioxide or nitrous oxide or nitrogen itself. So because air is containing both the nitrogen and oxygen. Okay, so the extra item that is going to be present in your producer gas when you are using air is nitrogen. Which of the following is a chemical method used for upgradation of pyrolysis bio-oil? So we know that bio-oil and biochar are the two major products formed during the pyrolysis product. Uh, but the quality of the bio-oil is very less when compared to diesel. It has very low heating value because of higher water content. So for the upgradation of the pyrolysis bio-oil, we use many chemical methods. So hydrotreating, solvent addition, filtration for char removal, emulsification with hydrocarbon. What is the method used in the chemical treatment? Right answer is hydrotreating. Okay. So others are the physical methods. Identify the type of incinerator. Fixed bed combustion, rotary kiln, fluidized bed combustion, bubbling fluidized bed. What is this one? What is this type of incinerator? So this type of incinerator is called as the rotary kiln. Okay, so it will be rotating in the horizontal axis. Okay, steel trays or days here, and materials, waste materials are fed through the hopper, and it is sliding down, passing through this rotating trays, and the heat energy is supplied from the burner in this direction. So heating of the waste material occurs. So the exhaust gases will be liberated from the incinerator like this, and then our finish the burning. Once the burning is completed, the finished products are passing out in this way. Okay, this tube is continuously rotating in the horizontal axis. Okay, this is happening in the rotary kiln. Identify A and B in the following process flow. So the feedstocks are size reduced, clean, dried, size reduced, and heated, and the melt feed is fed into A unit. Okay, and then it is going to the unit B. So in the unit B only, the pyrolysis gases, gasoline, kerosene, diesel are all formed. And from A only, carbon char is formed. What is A? What is B? Incineration pyrolyzer, distillation pyrolyzer, pyrolyzer distillation, gasifier separate. Just now we have seen this one, right? This is the pyrolyzer and this is the distillation unit. So the distillation unit is mainly separating the different products based upon the difference in their boiling point. That's why we are getting gasoline, kerosene, finally diesel. Okay. So this is the pyrolyzer and this is the distillation unit. Next, coming to the final question of assignment 11 sample question. In a fixed bed gasifier, air flow rate and feed flow rate are 15 Newton meter cube per second and 12 kg per second respectively. The feed material does not contain any sulfur, nitrogen, or chloride. The syngas contains carbon monoxide 40%, carbon dioxide 2%, hydrogen 30%, methane 5%, and C2H2 as that is ethylene as 2%. Now calculate the rate of production of syngas in Newton meter cube per kg of the feedstock. Okay, so they are asking you to find the syngas production. What is the amount of syngas produced? That too in the terms of Newton meter cube per kg. So no need for conversion of the units and all. You have Newton meter cubes per second and you have the kg. It's very simple to find the Newton meter cube per kg of the feedstock. The right answer is 4.7. We will look into the solution. Okay. So here we know that under the above condition, the rate of syngas production can be computed by the following equation. So this is the general equation. So here CO, carbon monoxide, carbon dioxide, hydrogen, CH4, C2H2. These are the possible products that can be formed during this gasification product. Okay, that is what given in the question. So we have to substitute the percentage here. Since these are all in percentage, just divide it with 100. Substitute the percentage here. Okay, so 40 by 100 is 0.4 and 2 by 100 is 0.02. 30 by 100 is 0.3 and methane is 5%. 5 by 100 is 0.05. C2H2 is 2%. So 2 by 100 is 0.02. Okay. Now air flow rate is given as, so the fixed bed gasifier air flow rate is 15 Newton meter cube per second. So substitute the air flow rate 15 here. 0.79 is constant. It is always constant in the formula. Multiply it with 0.79 and the feeding rate is 12. So it is also given in question 12 kg per second. So for per second 12 kg is fed. Okay. So substitute the 12 also here. So now it is very easy to solve this one. Uh, simplify all the thing 50, multiply 50 with 0.79 and add all these percentage and subtract it from 1, multiply it with 12. Okay, it will be 11.85 divided by 0.21 into 12. Okay, so the final value is 4.7 Newton meter cube kg of the feedstock. This is how we can calculate the amount of syngas produced after the gasification process. So please note on this formula, which is fuel gas produced is equal to air flow rate divided by the feeding rate into 1 minus the composition of the fuel gas. Okay, so do you have any doubt in this problem? Any doubts? Okay. If no doubts are there, we will move on to the tutorial problem. Okay. So the next problem is also similar to the previous one. So look at this question. In a MSW gasifier, air flow rate and feed flow rate. So again, the air flow rate is given as 10 Newton meter cube per second. Instead of 15, it is given as 10 here. And instead of 12 kg, the feed flow rate is 8 kg per second, respectively. So this is the air flow rate and the feed flow rate. Now, the MSW does not contain any sulfur, nitrogen, and chlorine. So our waste is not containing any of these components. So now we are going to check the composition of syngas. So the syngas contains the carbon monoxide 40%, carbon dioxide 2%, hydrogen 30%, methane 5%, C2H2 2%. Calculate the rate of syngas produced in Newton meter cube per kg of MSW. Okay, use the same equation, air flow rate into 0.79 divided by feeding rate into 1 minus the composition of the syngas. Okay, try solving this problem. It is similar to the previous problem. So try this one. Okay, we can substitute the values given in the question here. So the data given in question are 40%, so 0.4, 2%, so 0.02, 30%, so zero point 0.3, 5%, so 0.05, and 2% of C2H2, so 0.02. And the feed flow rate is 8 kg per second, substituted here 8. Air flow rate is 10, so 10 into 0.79 is 7.9. We add everything and subtract it from 1, it is 0.21, and 0.21 into 8. If you solve this one, it is together 4.702 Newton meter cube per kg of MSW. Okay, this is how we have to find the amount of fuel gas or syngas produced in the gasification process. So now the next question is, a country discards roughly 158 million tons of municipal solid waste. The high heating value of those discard is about 6000 BTU per LT. A mass burn waste to energy facility can convert those waste to electricity with a heat rate of 17,000 BTU of thermal input per kilowatt hour of electrical output. Roughly, this is the 20% efficiency. Estimate the electrical energy that could be produced per year if all of the discards were used in this type of waste treatment system. That is waste to energy system. Compare it with the total energy generated, which is about 4500 into 10 power 9 kilowatt hour per year. Okay, this is very simple question. We will look into the data once again. The amount of waste produced is 158 million ton. Okay, we know the amount of waste produced. This is for 1 year. Okay, and now the heating value is given. What is the energy content? That is the heating value in the discard means it is 6000 BTU per pounds. Okay, LB. So BTU per LB it is given. And then waste to energy facility can convert those waste to electricity. So these wastes can be burned and this energy from this waste can be converted into electricity. That electricity produced is from the waste is at the rate of how much heating rate is there means 17,000 BTU of thermal input per kilowatt hour of electrical output. Okay. So you are supplying 17,000 BTU input energy, okay, for every 1 kilowatt of electrical output. If we want to get 1 kilowatt of electrical output by burning the waste, we are giving the input energy of 17,000. Okay, roughly this is only 20 percentage. Okay, now estimate the electrical energy that could be produced per year if all of the discards were used in this type of waste to energy system. They are using all the 158 million tons for this type of electrical energy production, and totally if the energy generated is 4500 into 10 power 9 kilowatt hour per year. Okay, what would be the fraction of energy produced by using the municipal solid waste they are asking. First thing you have to find is the electrical output from the MSW. For that, first take the amount of the waste generated, which is 158 million tons per year. So into 10 power 6 ton per year, and multiply this much amount of the waste material is having the heating value of 6000 BTU per LB. So multiply it with 6000 BTU per LB. Now we are converting the LB to tons. So 1 ton is equal to 2000 LB. So multiply it with 2000 LB per ton and then divide it with the amount of heat energy given as the input, which is nothing but 17,000 BTU per kilowatt hour. You are providing this much energy and you are using this much waste mass. Now, how much electrical output is you are getting? Okay, after giving this much energy. So, if you solve this, you will obtain 111.5 into 10 power 9 kilowatt hour per year. This is the electrical output obtained by burning of the municipal solid waste. So here each year it is produced 4500 into 10 power 9 kilowatt hour. Okay. Now with the help of MSW alone you are producing 111.5 into 10 power 9 kilowatt hour energy. So just divide it to find the fraction of energy produced from MSW. So it is nothing but 0.024 into 100. It will give you 2.4 percentage. So out of 100 percentage of energy produced in a country, 2.4 percentage of electricity can be produced from the municipal solid waste. Okay. Is there any doubt? Okay. If no doubts, we'll move on to the next question. Estimate the landfill area needed to handle 1 year's MSW for a town of 2 lakh people. Assume per capita national average discard of 5 lb per day. No combustion, landfill density of 1000 lb per yard cube and 110-foot lift per year. So if it is getting buried, 110 foot is lifted per year. Assume 20 percentage of cell volume is soil used for the covering. Okay, so I will explain the question before solving this. So what is given is we need to find the landfill area. We have the 1 year's MSW of a town. Okay, that town is having nearly 2 lakh people. So we have to first find how much amount of waste is produced in the town itself. For that only it is mentioned, assume per capita national average discard of 5 pounds per day. So in a day, 5 pounds of waste are generated by one person. Okay, it is a per capita, one person, and we have 2 lakh people in the town. So first we need to find the total amount of this waste produced. And we have the density of the waste here as 1000 pound per air cube. So just we use all these data. So this is 2 lakh, okay, not 1 lakh. First, 5 pounds per day per person is generated. So multiply it with 365 days. So we will obtain for per year, and then multiply it with 2 lakh people, because only one person is producing 5 pounds. For the total village means we have to multiply the number of people in the village. So multiply it with 2 lakh and divide it with the density. Okay. So we will obtain the total amount, which is nothing but will obtain in volume. Okay. Density is equal to weight by volume. Now to find the volume, divide the weight with density. Okay. Totally the volume is 3,65,000 yard cube per year. Now only 80% of a cell is landfill. The volume of cell needed. So if this is the total area, our aim is to find the area required to fill it. Okay. So in this one, 20 percentage. So 20%, once this area is totally filled with the waste material, uh, okay, only 80 percentage is used for filling of the waste. So this 20 percentage area is left out to use this soil to cover up this entire area. Okay, that's what this 20 percentage is used. So whatever this volume we have identified is the area used for filling of the waste. To identify the entire waste, that is 100 percentage. For 80 percentage, it is 3,65,000 yard cube per year. Then for 100 percentage, how much? Just divide it with zero point 0.8. So you will obtain 4,56,250 yard cube per year. This is the total volume. Okay. Now the area of lift per year at 10 feet per year of depth is. Okay. So each year 10 feet lift is happen. Okay. Now you have to just find the lifted amount. Okay, so for that, now we know the total volume divided with 10 feet per year, which is the area lifted every year. Here the unit conversion is there. We are converting the yard to feet, so that yard cube to feet cube is you have to multiply it with 27. So the total area lifted is 12 lakh 31,870 75 feet square. Okay, and the actual sizing of the landfill would include a number of additional factors, such as additional area required for the road access and auxiliary facilities, reduction in the land fill volume as biological decomposition takes place, and increases as compaction as additional lifts are included. Okay, so now this is the theoretical calculation. What they are telling is, in this 100% area, there will be some areas left out for the road purposes, so that the vehicles can pass through this road. And then there will be some areas left out for the biological degradation. So what happens, that particular area will not be completely filled with the soil. Since it is biologically degraded, no need to fill it with the soil. So some amount of soil filling will not be there. So this is a theoretical value they are telling. This much amount of soil is required for lifting. That is what we have found out in the question. Okay. Any doubt in this problem? Okay. Coming to the next problem. So the next problem is, waste such as tires can be disposed of using a process known as pyrolysis. A car tire has a mass of 20 kg. 47% by mass of a car tire can be converted into carbon, and 25% by mass can be converted into gas. So 47% is converted to carbon, and 25% is converted into gas, which is nothing but methane. What volume of methane at room temperature and pressure is produced in the process if 80,000 tires are treated through the pyrolysis process. Okay. Question is very simple and direct. Like we are using a pyrolysis for process for the valorization of tires, and the mass of the tire is 20 kg. And if you are using the 20 kg mass of tire, and out of this 20 kg, 47 percentage of 20 kg is converted into carbon, and 25 percentage of 20 kg is converted into gas, mainly methane. Okay. They are asking if we are using the 80,000 tires during the pyrolysis process, how much amount of methane is produced at the room temperature and pressure during the pyrolysis process. Okay, this is the question. First, find the mass of the 80,000 tire. We know single tire mass is 20 kg. We are using 80,000 tires. So 80,000 into 20 uh, converted to grams. So 20 into 1000 is 20 kg. So 20,000 grams. So totally 16 into 10 power 8 grams. So this is the mass of the total tires. Okay. So now we need to find the volume of methane, right? So the percentage of methane converted is 25 percentage. So in the 16 into 10 power 8 gram of methane, 25 percentage is only converted. So 25 percentage means 25 by 100. So in 10 power 8, if you are dividing with the 10 power 2, that is 100 means it will become 10 power 6. And then we have to multiply the 25 with 16. Okay. So this is the total amount of methane that can be produced. Okay, from the data. Now we know that molecular mass of methane. So we know methane molecular formula is CH4, right? So H is 4, C is 12. So the molecular mass is 16. Okay. To find the moles of methane, moles is equal to moles. Moles is represented with small n. Moles is equal to weight by molecular weight. There is nothing but mass by molecular mass. So now we know that how much amount of methane is there. 25 into 16 into 10 power 6. So 25 into 16 into 10 power 6. That much gram of methane is there. Divided by the molecular weight. Molecular weight is again 60. So divide it with 60. Okay, 16 will get cancelled. So that 25 into 10 power 6 moles of methane is produced. Now, at the standard temperature and pressure condition, 1 mole of methane occupies this much volume. That is nothing but 22.4 dm cube. Okay. So 22.4 dm cube is produced for 1 mole. For 25 into 10 power 6 mole, just multiply it. You will obtain 5.6 into 10 power 8 dm cube. Now the unit conversion happens. So that 10 power 3 will be removed. 1 dm cube is equal to 1000 meter cube. So 1000 will be removed. So here 5.6 into 10 power 5 meter cube of methane is produced at the standard temperature and volume. Now the question is to find the volume of methane at the room temperature and pressure. Okay. So for 25 degrees Celsius, we know that for 25 degrees Celsius, 5.6 into 10 power 5 meter cube volume of methane gas is produced. Then for room temperature 30 degrees Celsius, how much methane is produced? So convert this to Kelvin at 273. So convert this. So here you will obtain, okay, 303. So 273 plus 30 is 303. And then it is 0 degrees Celsius, not 25. Okay. So here add 30 with 273. Then you will get 303. So 303 divided by 273 is nothing but 1.1098, and then multiply it with 5.6. You will obtain 6.215 into 10 power 5 meter cube. This is the actual volume of methane produced at the room temperature. Okay. So standard temperature is 273 Kelvin. For room temperature means 30 plus 273 is 303. We are finding it for room temperature. Any doubt in this question? Any doubt so far? Shall we continue? Okay. So coming to the next question. A pyrolysis plant handles 0.5 TPD municipal solid waste and producer gas, char and liquor. Operating temperature is 788 degrees Celsius and the pressure of the reactor is 1 atmosphere respectively. The gas composition in terms of volume percentage is hydrogen 39.1, carbon monoxide 33.5, methane is 13.1, carbon dioxide is 14.3. The mass percentage of production of gas, char and oil are 35, 20 and 45 respectively. Determine the moles of each component of gas produced per day. So what are the moles of the each component of the gas produced? They are asking. Like they have given the gas composition, which includes the hydrogen, carbon monoxide, methane, and carbon dioxide. Okay, but in terms of moles, these are in volume percentage. In terms of mole, they are asking how much moles of hydrogen, carbon monoxide, methane, and carbon dioxide are produced. Okay, it's very simple. First. From the beginning we will solve it on the basis 500 kg of MSW per day. So we are taking 500 kg MSW per day. So in this one the amount of solid liquid gas product formed is given. Okay, 35, 20 and 45 are the percentage of gas, char and oil. So out of the 500 kg, 35 percentage means 175 kg is the gas produced. And out of 500, 20 percentage means 100 kg of char is produced. And then out of 500, 45 percentage means 225 kg of oil is produced. Okay. So if you add this, you will obtain 500 totally. 500 kg will be there. And the average mole weight of the gas produced. Now we are going to find the average mole weight. Okay. So since 39.1 percentage of hydrogen is formed, we are going to find this is in percentage. So divided with 100 and the molecular weight of hydrogen is 2. So 0.391 into 2. And carbon monoxide molecular weight is 12 plus 16 is 28 and that 3.5 divided by 100 is 0.335. Okay. And then methane molecular weight is 12 plus 4 16. So 16 into 0.131. Then carbon dioxide is 12 plus 32, which is nothing but 44 into 14.3 by 100 is 0.143. If you add everything together, you will obtain 18.55 kg per mole. This is the total amount of the gas produced in terms of kg per kilomole. Okay. Now, the gas produced in kilomole per day. To obtain the gas produced in kilomole per day, we know that the product produced from the municipal solid waste contain gaseous product, solid product biochar, and the liquid product oil. Okay, out of these three, the amount of gas products produced are 175 kg per day. So 175 kgs are produced. Okay. So for 1 kilomole, 18.55 kg are produced. Okay. For 175 kg, how many kilomoles are produced in a day? Just multiply the 175 into 1 by 18.55 so that you will obtain 9.43 kilomole per day. So in a day together, you are converting this gas in from kg to moles. Okay, that is what happened. To convert it to mole, divide the weight by molecular weight. Now you know the weight of the gas produced. Now you also know the molecular weight of the all the gases together. Okay, so divide the weight with molecular weight. You'll obtain 9.43 kilomole per day. Now you know the total moles produced as the gas during the pyrolysis process. Individual moles, number of moles of hydrogen, carbon monoxide, methane, and carbon dioxide are to be found. That is the exact question asked. So now you use the mole basis for solving. So totally 9.43 kilomoles are produced in a day. In this, only 39.1 percentage is hydrogen. So multiply it with 0.391. So we'll obtain 3.69 kilomole per day. And then carbon dioxide produces 9.43 out of 9.43, only 33.5 percentage. So 0.0335 you have to multiply, you will obtain 3.16 kilomole. So amount of methane produced is 13.1 percentage. So multiply it with 9.43, you will obtain 1.24 kilomoles. Then carbon dioxide produced is 14.3 into 9.43 by 100. So it is 1.35 kilomole per day. First, you are finding the mass of the gas, char, and oil produced from the municipal solid waste, and then you are finding the first you have found the mass of the gas. Now you are finding the molecular weight, average molecular weight of all gases together. Now divide the mass by the molecular weight. We'll obtain the moles in kilomoles per day. This is the average of all the gases. Okay. Now find the individual moles of hydrogen, carbon dioxide, methane, and carbon dioxide by multiply these volume percentage with the total amount of moles produced in the day. Okay. Is there any doubt in this problem? Any doubt? Okay. We will move on to the next problem. The next problem is a dry municipal solid waste has the following composition on mass basis. So this is the composition of municipal solid waste. Carbon 40 percentage, hydrogen 5 percentage, oxygen 30 percentage, and ash 25 percentage. Determine the stoichiometric oxygen requirement for the combustion of the municipal solid waste. Assume the ash as inert and average molecular weight of the ash is 56, and if the ratio of nitrogen to oxygen in air is 4 is to 1, determine the stoichiometric requirement of air. So here you are using the municipal solid waste and you are going to combust the municipal solid waste. The typical composition of the waste is it is having the carbon, hydrogen, oxygen, and ash in terms of 45, 30, and 25 percentage. Now we are using the uh, municipal solid waste to combust it and then to produce the respective gases. Okay, for the combustion you are using the air as the product. Okay, so you are using the air. In the air it is given nitrogen to oxygen ratio is 4 is to 1. Okay, now whatever the ash present in our waste is again formed as the ash itself, so it is given as inert. Okay, you can eliminate it during the stoichiometric calculation. Exact question asked here is, okay, molecular weight of ash is also given, which is 56. Now the exact question asked is to completely combust the waste into the gaseous product, the amount of oxygen required stoichiometrically. Okay, that is what we need to determine. For that, we are going to do the stoichiometric balance. First, assume that initially we are having 100 grams of MSW. Okay, so we are having 100 grams of municipal solid waste. 40% is carbon. Okay, so 5% is hydrogen, 30% is oxygen, and 25% is ash. Before that, we are going to find the moles of each and every component. So to find the moles, we have the weight percentage. To find the mole, divide the weight with, so moles is equal to weight by molecular weight. We know the weight of the carbon is 40 percentage. So molecular weight is 12. 40 by 12 is 3.33 moles. Hydrogen, the weight is 5 percentage. So 5, molecular weight is 1. 5 by 1 is 5 moles. Oxygen molecular weight is 16, total weight is 30. So 30 by 16 is 1.875 mole. Ash is 25 gram and the molecular weight is given in the question itself. So 25 by 56 is 0.4464 moles. Now we have found the mole composition of the waste, municipal solid waste. So with these moles, we can easily find the molecular formula of the municipal solid waste. Before going for the stoichiometric balance, these moles are required to write the equation. Okay. Now we have found the molecular formula of MSW. So write the stoichiometric equation. So when this municipal solid waste is burnt in the presence of oxygen, the possible product that can be formed is from the carbon dioxide can be formed. From the hydrogen, water will be formed. Again, oxygen will combine with the hydrogen to form the water, and oxygen with carbon will form the carbon dioxide. And whatever ash is here, it is given that ash is inert component. Okay, ash is again formed as the ash itself. Okay, this is the equation. So here A, B, C, G are all known values. So A is 3.3, B is 5, C is 1.875. Already we have obtained the molecular formula itself. So now we are going to balance the equation. Okay. Since this G is again converted into same quantity of G, we are avoiding the we are eliminating the ash from the equation. So rewriting the equation as CaHBOC plus DO2 is equal to EH2O plus FCO2. Since ash is the inert component, like it is not reacting. Whatever ash is there in the biomass, it is again coming as the ash itself. Okay. Now you know that A is equal to F because carbon is only here and here. So A is equal to F. We know the value of A, right? A is 3.3, so F is also 3.3. And you are balancing the hydrogen next. First the carbon is balanced, next balance the hydrogen. So here you have only hydrogen, one hydrogen here. So in front it is 1. So 1 into B is B. B is equal to 2 hydrogens are here. So 2 into E is 2E. You already know the value of B. So value of B is 5. Already we have obtained the molecular formula, right? So B is 5. So B is equal to 2E. So E is equal to B by 2. B divided by 2 means 5 divided by 2 is 2.5. Now you also know the E value. Then you go to the C. Oxygen formed is C value is 1.875. So here 1 into C is C, oxygen balance is here. 1 into C is C, and then you have oxygen here also. 2 into D is 2D is equal to 1 into E is E plus 2 into F is 2F. Okay, this is the oxygen balance. Now, you know all the values, like you know you already know the C value. C is 1.875. So C value is known, and you know the E value from B, it is 2.5. You know the F value, A and F are same 3.3. Substitute all the values here to find the unknown value of 2D. 2D is 7.285. So D is 3.645. Now we have found uh, we have balanced the stoichiometric equation. We have found the A, B, C, D, E, F, okay, in the equation. Our aim is to find the uh, amount of air required, okay, amount of air required using the stoichiometric equation. Now you know that D is the amount of oxygen required. So what is the value of D? 3.645. 6425. This much moles are required. So to find the mass, just we know that moles is equal to weight by molecular weight. To find the weight, that is the mass of oxygen required, multiply the moles with the molecular weight. Molecular weight of O2 is 32. So 3.645 into 32 is 116.56 gram. So this much amount of oxygen is required. Okay, for 100 gram of municipal solid waste conversion. Okay. So So for 100 grams of municipal solid waste conversion, we require 116.56 grams of pure oxygen. Okay, but in the question it is already given, determine the stoichiometric requirement of air. So if we are using the air is comprised of both nitrogen and oxygen. The ratio of nitrogen to oxygen is given as 4:1. Okay. So now we have to find the nitrogen in the air also. So if 3.6425 moles of oxygen are required, this is the one part, okay. N2O is, ratio is N2O2. Ratio of nitrogen to oxygen is 4:1. Okay, so 4 divided by 1. For one part, 4 parts of nitrogen is required. If 3.6425 is the mole of the oxygen, then into 4 is the moles of the nitrogen. Okay, so N2 in the air containing 3.6425 moles of oxygen is equal to 4 into 3.6425, which is nothing but 14.57 moles. This is the mole of oxygen. Again, you know the mole. To find the mass of the nitrogen, sorry, this is the mole of nitrogen. So you know the moles, to find the mass multiplied with the molecular weight. Molecular weight. So molecular weight of nitrogen is 14 into 2, 28. So 14.57 into 28 will give you 407.96 gram. This is the mass of the nitrogen. So air is comprised of nitrogen and oxygen. You know the weight of the, that is the mass of the oxygen, mass of the nitrogen. Add these both to find the mass of the air required. Okay, so 407.96 plus 116.56 is 524.52 gram. This much mass of air is required for the complete combustion of 100 gram of municipal solid waste. Okay, so this is the stoichiometric requirement of air. Any doubt in this question? Any doubts so far in today's session, in the tutorial problems, sample assignment question? Any doubts so far? Okay. If no doubts are there, thank you. Thank you for joining today's session. We'll meet you in the next session on next Saturday. Thank you.